Okay, off we go. So we stopped down here talking about Python, all the cool stuff that you can do with it. I gave you a cheat sheet that was here. If you didn't see it yet, please use that on the final. But let me open it because I think there's one more thing that we need to look at. So we did conditionals, loops. Last thing is functions. So when you make a function, remember, you got to say def, the name of the function, give a bunch of parameters, comma separated. Maybe there are no parameters. And then you say colon, indent, body, that sad face is always there, okay? And if you want to give back something from your function, you have to say return. I'll give something back to the person who called your function. And when you call a function, you just say its name. You just say its name, give the arguments to be placed into the parameters, and then maybe it gives something back. You can save it away for later. Okay, so it's all nice and color-coded. Please read it in your spare time if you can. Param1 is going to get set to arg1. Param2 is going to get set to arg2 when you run the function here. Okay. It starts running the body. That's what it means to run the function. Runs the body with the parameters set to the arguments. Okay, and if your function just does something, you can just call it on a line by itself. But if it gives something back, you better use that result. Maybe save it around in a variable. Okay, so yeah, I have just a bunch of examples of functions because functions are just a nice way of making a bunch of stuff and putting things together. It's a nice way to summarize everything that we did in this class. So yeah, let's talk about my first example function. Let's make the simplest kind of encryption function. So back in the Greek era, when Caesar was around, we had the Caesar cipher, where you just shift every character in the alphabet by 13, so A becomes N, and if you ever run off the end of the alphabet, you start all over again, so N also becomes A. So B becomes O, O becomes B, vice versa. And so if you were trying to encrypt hello, it would give you back uryb, right? Remember all that? So let's do this. Let's make an encryption function. Let's make a ROT13 function. It's the other word for this, also called the Caesar cipher. But let's make that as a function and have it give back a encrypted function, or encrypted string. Does that make sense? So ROT13, aka Caesar cipher that we talked about. It's doing this process. Shift every letter of the alphabet by 13. Hello becomes uryb. If you do it again on uryb, it comes back to hello, though. That's why it's 13. It's always halfway through the alphabet. It becomes its own inverse. That's quite nice. So, yeah, let's do this. Let's use two functions. That'll make it easier on us, because I'd like to do this. Let me, let's see. Let's do it this way. Let me start the file. This is lecture 32. And then I'll show you how I want to use this function, and then we'll make it. So I'll open up idle. I already forgot the number of this lecture. 32. So a new file. I'll call it rot13.py, and I'll save it where you can have it. Lecture 32 folder. There we go. So here's how I want to use this. I would like to have the user enter something, enter a string to encrypt. And we'll just do all capital letters. Let's ask the user to enter in a string that consists of all capital letters. And then we'll get that with the input function. Let's save that away, call it text or something. And then what we'd like to do is call our function, rot13, on text, and print whatever that is out. If we typed hello all caps, it will print out uryb. That's the idea. So that's what we'd like to do. And this is how we want to use this function. To make it easier on us, let's make two functions. Let's make one like rot13 that encrypts the entire string. We'll call that rot13 string. And then we'll make another rot13 function that encrypts a single character. because we'll have to call that a bunch of times for every character in our string. Does that make sense? That's how we'll do it. So, yeah, let's get that working. So def rot 13 string, given some text. How do we want to do this? Well, we'd like to form a string that is the encrypted version of this text. Does that make sense? So we want to like read through our text. Maybe the text variable really was all caps hello. We'd like to build up the string like encrypted string. We'd like to build up variable somehow. And we'll encrypt a single character at a time. Let's pretend we can. That's the beauty of making functions. You can just pretend it exists and then you'll go make it later. So let's do that. Let's build up an encrypted string consisting of all the characters of the text string encrypted. So how do you do that? You have to go through, you have to iterate through the string. So let's build up encrypted string. Let's start it empty, and then we'll eventually return that. So we're going to put a bunch of characters, a bunch of encrypted characters, one for every character of text, into this encrypted string variable. And so here's the idea. Let's go through every character in text and encrypt it. We'll have a function that encrypts a single character. Okay, so for, you can use a for in loop on a string. You can think of it as just a list of characters. So for every C in text, C will get a chance at being every character in the text string. Let's encrypt that character, encrypted C, encrypted, we'll call it char, I guess. Encrypted char equals rot 13 on a single character, C. Okay, so we'll encrypt that one character that we just saw. Maybe it was the capital H. We'll try every character though. And then once we've got the encrypted form of it, the encrypted form of H was U, right? We will take that U and we will add it to the end of our encrypted string, which started out empty. And so that's how we can add more things. We'll next see the E and encrypt that to an R. We'll add that to the end of our string, which just has a U in it. So we'll build up this final answer one character at a time, always adding to the end. So encrypted string equals whatever it was before. Maybe it was empty, maybe it had something in it, plus this new encrypted character right at the end. All right? So if only we had this rot13 char function that would encrypt a single character, this would work. Any questions about this so far? Because the last piece of the puzzle is to encrypt a single character. How do you do that? So def rot13 char, you take a single character called C, and you do something, you encrypt that character C. And here's the simplest way that I can think of to encrypt every character. What you do is you can make two lists of characters, which are essentially strings. So make two strings. You'll make like a chars string and an encrypted chars string. And here's how you'll do this. You'll make chars just the alphabet. So like A, then B, then C, then D, then E, then F, dot, dot, dot. And you'll make encrypted chars the encrypted form of the alphabet in order. So they all correspond. So the encrypted form of A in the same location would be the N. Does that make sense? So we'll put an N here. The encrypted form of B will be O. Put an O there. Then P. Then Q. Then R. Dot, dot, dot. And the idea is, we see a character and we need to encrypt it. We'll look it up in the chars string. We'll find it, like maybe we're trying to encrypt the letter E. We'll find its index. We'll notice that it's 0, 1, 2, 3, 4 in the chars array, or in the chars, string. We'll go to index 4, we'll go to the fourth character in the encrypted chars string, and get out the R. So that's how we'll look it up. We'll go through chars, figure out which index, and extract the encrypted character from the encrypted chars string at the same index. That's how we'll do it. So we'll find, like, I don't know, This is index 4. We'll also go to index 4 here. That's how we'll do it. So let's make those two strings. Give me a second while I type them all. So chars is equal to A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. And encrypted chars is equal to the string of all the encrypted characters. So what does A match with? It matches with N, and it goes in order. So N, O, P, Q, R, S, T, U, V, W, X, Y, Z, and then it starts over again. A, B, C, D, E, F, G, H, I, J, K, L, M. And in theory, there's 26 of each of these, and they all correspond. So every time I have a character that I need to encrypt, I'll look it up in the char string. Which index is that? Like maybe I'm trying to encrypt the H. I'll look it up, and I'll remember its index, and then I'll go to the encrypted char string and go to the same index and extract my encrypted form. So that makes the H go to U. That's how we'll do that. So if only, so I have this char C that I need to, this character C that I need to encrypt. I need to find the index of C in chars, and then go to that same index in encrypted chars. That will give me the character that this one corresponds to. Okay, so here's how you look through every index to find the character that you're looking for. So let's start some iteration variable at 0. And let's save the index where we find the thing, I guess. Index of char. Let's make it -1. That never exists. Hopefully we'll find something. So we would like to go through, iterate through every possible index in char. So index 0, 1, 1, one's 1, then 2, then 3, all the way to index 25, right? How can you easily get which is the last valid index? You want I to always be less than the length of the char string. Because the length is 26, you want it to stay smaller than that. And what you want to do is we got to set this index of char. Figure out which index holds the character that we care about. So if chars of I, or whatever I is now, maybe I is this number that makes H, or maybe it's 4 that gives us the E, we want to encrypt and make it R. So if chars of I is equal to the character I'm trying to encrypt, then save that index. Index of char equals I. And now I have it saved for later. And only one time will this if ever work. So once you find it, you could use break like I showed you last time, or you could just let it continue. I equals I plus 1. If we didn't find it here, if it wasn't A, maybe it was B, make I one more, so we can go and look at that index of chars and potentially save its index, if that was the character we're trying to encrypt. All right? So once this while loop completes, we will hopefully, if it was any of these characters, we would have found its index and we would have saved it in this index of char variable. All that we need to do now is take that index and go to the same one, like if we found the index of H, go to the same index in the string encrypted chars. Return encrypted chars at that same index of char. And that will encrypt like the H to the U, the E to the R. Any questions on what this loop is doing? Does that make enough sense? It's finding the index of C in the chars string and going to the same index, that's what we're returning, in the encrypted chars string. And so all together now, if we run this, we can type in hello and get out Uryb. Yay. Whee. So that is the program. I made a function that encrypts all the characters in an entire string using the Caesar cipher. Any questions about any of that? Alright, so that's just a starting example of functions. Let's do some cooler stuff. Let's talk about randomness. So, you guys remember what Etch-a-Sketches are? Did you have those as children? I don't know. I did. It's that thing with the little window and the little knobs that you can turn and it like goes left and right depending on which way you turn the knobs. Let's make that in Turtle Land. Let's make this. And so let's make a random Etch-a-Sketch where we have the turtle like draw a bunch of random lines and turn in random directions. And we'll make some cool stuff from that. Okay? Oops. Oh gosh. Go away. No? There we go. So we'll use the random library for this. And when we'll have to figure out when to stop the program as well, but we'll figure that out in just a second. So let's call this etch-a-sketch.py or something like that. And we'll import turtle, and we'll also import random. Turtle.speed, super fast. We're trying to get through a lot today. And then turtle.shape, of course, better be turtle. And so here's what we can do. While true, just forever, we can tell the turtle to just, how do you make a random etch-a-sketch? How do you draw random lines? You just tell the turtle to go forward by some random amount and then like turn in a random direction. You can also turn straight around if you want to. So that's pretty easy. Go forward by a random amount and then also turn by a random, let's make it always a 90-degree turn, by a random multiple of 90 degrees. So this will be fun. So turtle.forward. Let's go forward by a random amount. Random.randint. That gives you a random integer within a range. Let's go like 10, 50. So some line length between 10 and 50 units. And then we'll turn turtle.left. It doesn't matter, left or right, because we'll turn every option. Some multiple of 90 degrees. 90 times random.randint. Something between 0 and 3, right? Because if you make it 360, you didn't change at all, so you want it to be either 0, 0, 90, 180, or 270. So just these few lines make some really cool abstract art. So this is an example of randomness. Whee, there he goes. He's drawing some weird stuff. And this program never stops. Maybe one thing that we can do, because now the turtle's off the screen, he's not doing anything useful anymore. Maybe once the turtle like goes off the screen, we can stop the program. How about that? Whee, there he goes. But he's drawing some cool stuff until he gets off the screen. So we can change this true to make sure like he's always within some bound. Let's stop drawing when the turtle runs outside of like maybe not 600 by 600, but let's do it like 300 by. Or no, yeah, 600 by 600 works because it's 300 on every quarter. So let's make sure that the turtle only draws his random lines between within a 600 by 600 box, centered at 0, 0. So he can't go any farther than like 300, 300, or lower than negative 300, negative 300. Okay, so you can get at the turtle's current X and Y coordinate like this. Python turtle. You can ask the turtle, where am I? Or where are you? By calling these functions. Where are they? Turtle's position. You can call pause, turtle.pause, to go to get the turtle's current X and Y coordinate as a tuple. Or you can say turtle.xcore to get the current X coordinate, and then turtle.y core to get the turtle's current Y coordinate. So we'll just use those. It's slightly simpler for this example. So while turtle.xcore is like it's within the range, right? So x better be within negative 300 and 300, and also y should be within negative 300 and positive 300. And so you can do it like this. Python. You can't do this in C++, but you can do this in Python if you've taken another programming class before. I can put inequalities on both sides in Python. While turtle.x coordinate is within negative 300 and 300. Isn't that nice? That's something you'd really like to be able to do in other languages, but some other languages don't let you. And then we also want the same to be true for the y coordinate. Whee! So while the x-coordinate is within this range and the y-coordinate is within this range, keep going forward. But once you get out of that range, turtle, you're done. We're going to stop the program. Whee! And so then the program just stopped and we made this beautiful abstract art right here. Are there any questions about this silly program? Yes?
So you couldn't do that in C++ with the AND?
You would have to use an AND to do this. You can't like say this is less than this at the same time. You can't write this exact syntax. You'd have to split it up with an AND, yeah. But this is more mathematical, I guess. It's prettier. If only we could do that in C++. Any other questions? All right, pretty drawings. Let's continue with them. Oh, this is a super cool one. Let me show you this. This one doesn't involve any drawings, but it's going to require an explanation in terms of drawings. There's no turtle involved, but you can imagine a turtle. Let's make a new file. I'll call it darts.py. So we're going to make a simulation, and that simulation is going to give us pi. It's going to compute an approximate value for pi. It's really, really cool how this is going to work. Let me make some room on this slide for me to draw all about it. I guess this doesn't have to be huge. Go like that. Squeeze this over here. There we go, that's enough room. Here's the idea. You can approximate pi by pretending to throw darts at a unit circle. So here it is. Pretend that you have a dartboard. And a dartboard is a perfect circle, right? Let's pretend it's a perfect unit circle. So here's like 0, 0, and the circle that is our dartboard is radius 1. So this is like, let's see, this is radius 1, which means that this entire box that surrounds it, you can also draw a box around that circle. That's 2 by 2, right? 2 by 2. It's a 2 by 2 box around a circle of radius 1, diameter 2, of course. Here's the game. You can throw a dart anywhere on this dartboard, including the box. So you can throw a dart, it might hit here, somewhere in the circle, or it might hit here, somewhere outside of the circle. And you can, believe it or not, you can approximate pi by pretending to throw darts somewhere within this box and counting the number of ones that land within the circle and the ones that don't land in the circle. It has to do with the ratio area. So if you throw a bunch of random darts at this 2 by 2 box, some of them are going to randomly fall within the unit circle, and some of them are going to randomly fall outside of the unit circle, right? The question is how many? How many are going to, on average, as you approach infinity, how many are going to land inside the circle and how many are going to land outside? And the question has to do with areas. Like, well, it has to do with areas. What's the area of the circle? The area of this unit circle, it's pi r squared, right? So pi times 1 squared, which is just pi. It's a ratio. It's like the area of this, just the circle, over the area of the whole thing. That's the ratio of how many are going to appear in the circle, because it's random. So what's the area of the circle? It is pi. What's the area of the whole box that surrounds it? That's just 2 by 2, right? So 2 squared equals 4. So the ratio of darts, if you randomly throw darts blindfolded at this box, the ratio of ones that are going to fall inside of the circle is going to be pi over 4. Because the area of this is pi, and the area of the whole thing is 4. So pi over 4, every pi out of 4 darts are going to land inside of that circle. Does that make enough sense? It's a ratio of areas. If you pick random darts, it's just how much space do you have. So the number of darts that hit inside the circle over the number of darts total will approximate pi over 4. And so if we multiply whatever we get, like counting these things, if we multiply this answer, because it's supposed to approximate pi over 4 by pi, or by 4, it will give us pi. If we multiply that by 4, it gives us pi. This is really cool. So we're going to essentially do this. We're going to pick a bunch of random points in this rectangle, in this 2 by 2 rectangle, and count how many are inside the circle, count how many are outside. how many darts that we threw. And if we multiply by 4, we will get a good approximation for pi if we throw infinite darts. So let's see here. We have to throw a lot of darts to get a good approximation, though. So total darts, let's throw randomly 1,000,000 darts. So total darts is 1,000,000, and we also want to keep track of how many darts landed inside of the circle. Darts inside circle. Of course, when we haven't thrown anything, it starts at 0. And then we want to throw this many darts. Throw total darts. Maybe it's 1,000,000, maybe it's 100. So for I in range, total darts. That will range between 0 and 999,999, but it will be 1,000,000 times total. So 1,000,000 times I would like to throw a single dart and then see if it landed inside the circle. All right, so how do you throw a dart? You have to, well, if it's going to be within here and it's random, it's just you pick a random x coordinate and a random y coordinate, and that is where your dart landed. So x equals random dot. If you want a random floating point number, a random float, a number with decimals, you say not random dot randint, you say random dot uniform, and then you give your range. So I want the x value to be between -1 and +1, and same for the y value. That will give me a random number within a random point within this unit box, I guess. I don't know. So that is my dart. I just threw it. It gave me a random x coordinate and a random y coordinate. And we need to see if this dart landed inside of the circle. Or maybe it was outside of it. How do you check if an xy coordinate landed inside of a circle? You have to go back to math and think about what it means to be inside of this circle. How do you graph a filled-in circle on the graph? Do you remember the equation for a normal circle? It's x squared plus y squared. If it's radius 1, it's just equals r squared, right? So equals 1 squared equals 1. If we want all the points that are within the circle, it's equals 1 or anything less than it 2. This is essentially calculating the distance. The distance of any point is equal to 1 if you're on the circle, but if you're inside, the distance from the origin is less than or equal to 1. So if this is true for our dart, it means it was inside of the circle. If x squared plus y squared is less than or equal to 1. If x squared, x times x, plus y times y is less than or equal to 1.0, then it landed inside of the circle. So darts inside circle equals 1 more than it used to be. Otherwise, we just don't add it. Okay, so after we've thrown 1,000,000 random darts and we counted which ones landed in the circle, we can calculate pi. So print this ratio, the number of darts that hit inside the circle, so print darts inside circle over total darts that we threw. And then if we multiply that by 4, that gives us pi. Because it gives us originally an approximation of pi over 4. So if we multiply this answer by 4, that should give us an approximation for pi. Run module. And it's not a very good approximation, but if you throw enough darts, it'll give you a perfect approximation. So we got 3.1415. That's pretty good. If you run it again, it's random. It's going to throw darts in a different way, and it might not be as good. 3.1408. It's at least good to 2 decimal places. Let's try throwing 10,000,000 darts. Let's see how much better that gets. It takes longer, of course. 10 times the amount of time. It's got to try 10 times more darts. You can do it. Yay! So I guess it has about 3 decimal places of precision now. 3.141. But this is just another example of using randomness. So random.uniform gives you a random floating point number. Any questions about this example? That's one way to calculate pi. You throw a bunch of random darts and you count how many landed inside the unit circle. The ratio of areas gives you pi over 4, and multiply it by 4, you get an approximation for pi. Just fun to think about. All right, next example. I would like to have 2 slides dedicated to the target logo because it's a fun little thing to draw. And also, when I was going to grad school at UCSB, for my first 5 years that I was there, they did not have a Target. Within like an hour drive, it was horrible. There was only a Kmart. It was the second highest grossing Kmart in the country after the one that was in Hawaii. Because there was nowhere else you can go, and it was just horrible, horrible times. And I was so happy. My last year, they made a Target. So we're going to honor Target by drawing its logo a few times. So let's make it simple. Let's draw a square Target logo first, and that'll give us some practice with the turtle library and also making some functions. So functions to the rescue. If only we could have a draw square function with a center, a width, because the height is the same as the width, and a color. Here's how you could draw a Target logo. First, the order really matters. First, you draw this box, draw it fully red. So now you just have a red box. Then you draw this smaller box, fill it white. So now you've like cut out the middle. And then you draw this even smaller box and color it red again. Now you have a Target logo. That's the idea. So yeah, those are the 3 things that we need to draw a square. Because the center is going to change, the width's going to change, the color is going to change each time. Okay? Apparently, a good amount to make this work and look good is this outer box is 200, this white box is 125, and this inner box is size 50. Okay, so they're all going to be centered at 0, 0. Let's do that. That's easy. And then let's figure out how to draw a square from there. So let's draw a Target logo that is made of squares. Target square.py. So if we take this into account, if we could just draw a square centered at 0, 0, the first one is width 200, and the color is red. If we did that, and then 2 more, a 125 square, and then also at 0, 0, colored white, and then finally a size 50 square, also at 0, 0, colored red, that will make our Target logo. So we need to make the draw square function now. Let's make that happen. Def draw square, and it takes center, width, and color. So we're trying to draw a filled box. Okay, we're trying to draw a filled box here. I guess we like to set the pen color as well. No, let's just do the fill then. How do you do this? So we need to essentially draw a filled rectangle. We know how to draw rectangles, right? But we knew how to draw rectangles given the corner, right? We knew like the upper left corner or something. So how do we get like from the center to the upper left corner of a box? If we're asked to draw a size 200 by 200 box, how do we get to the upper left corner of that? Well, it's you start in the center and you go over by half of its width. Does that make sense? So this is like 100. And then you go up by half of its width again. That's another 100. And that will give you the upper left coordinate. The upper left coordinate is your center. Your center's x, right? Go left by 100, which is half of your height. Center x minus width over 2. And then the y coordinate is the same idea. The y coordinate is up here. It was center's y plus half of your width. Center y plus half your width. Width over 2. Okay? And this is your center point. That's your center x, center y. And so once you get to the upper left, you know how to draw a box from there. You just like face right, go the width, turn left, turn right by 90, go the width, turn right by 90, go the width, etc., etc. So that will mostly get us there. So we need to calculate the upper left coordinate. So what is center x? Center x is take center, it's a tuple, go to the x coordinate, that's the 0th element, right, of center, center 0. Center's y coordinate is the other thing in the tuple, this thing, it's index 1, center 1. So that means upper left, the upper left coordinate is center x minus width over 2, and then center y plus width over 2. We can tell the turtle now to go there. Turtle dot up, turtle dot go to UL. We just calculated the starting coordinate. Turtle dot face right, right? Face east, so set heading 0, I guess. Turtle, put yourself down so that we can draw stuff. Turtle dot down. And then if we want to draw with a certain color, it's the fill color. So turtle dot fill color, whatever the color that was passed to us was. And so now we can draw our square, remembering to put around our drawing turtle dot begin fill and end fill. Don't forget that, otherwise it won't fill it in. So now in between these, we can actually finally draw our square, which is going to be turtle dot forward by width, and turtle dot, we start at the upper left, we just ended in the right coordinate, we need to turn right by 90. Forward by the width some more. And then this last one is not really necessary. So that should draw our square. Begin fill, end fill. With these 3, that should give us a square target logo. Yay, look at it. Any questions about that? So I made a draw square function so that we could reuse it. We use the center this time instead of UL because that makes more sense for a target logo at least. But we calculated the upper left from the center. Not too bad, I hope. Okay. Let's draw the real target logo now. Let's draw it with a circle. So it's a bit weird to draw a circle in Turtle Land. Turtle dot, is it just circle, I think? I believe, yeah. You can draw a circle with the turtle with the dot circle function. You give it a radius. That's like the radius of the circle that you want to draw, and it will draw it. But the weird thing is, you don't put the turtle in the center of the circle that you want to draw. You have to put the turtle at the bottom of the circle that you want to draw. So the turtle needs to start here, and then you say turtle.circle with the radius, and then it'll actually draw it all above where it currently is. So if we're giving the center point of our circle, we have to move the turtle down to here, and that's when we can use the turtle.circle function. Okay, that's the idea. So let me show you that, and then let's make it work in a little bit of a cooler way. So let me copy everything from target square, and I'll make a new file. I'll call it like target improved. So we'll take our draw square. Let's change it to draw circle. Draw a circle, and draw a circle with a center, width, and color. It'll all be the same as the draw square calls, right? So let's take these, copy them, change them to draw circle, and just as easily, we'll be able to draw a circular target logo because the center is the same, the width, which is the radius now, is the same, the color is the same. We just need to change this draw circle function to actually draw the circle. So in order to draw a circle, we have to move down. We have to move the turtle down from the center where we're given, where we go to. Move the turtle down by the width. And no, yeah, sorry, it's by the width over 2, I believe. That's what we would like. So how do we want this happen? Yeah, so our starting coordinate is going to be, like, this is center x, center y. It's going to be same x, center x, but it's going to be center y minus width over 2. And I guess we're given the diameter. The width is the diameter of the circle. So the radius is width over 2, really. So we would like to starting point is center x, comma, center y minus width over 2, because the turtle needs to be at the bottom of the circle that we're about to draw. And then turtle go there, set heading, whatever you want, doesn't really matter. Fill color. Then you just say turtle.circle. That's all. And it's width over 2. Width over 2 is the radius of this circle, because the width is supposed to be like from here to here. That length, that's the diameter, so half of that is the radius. And that's what the dot circle function expects. It expects the radius. So just as easily, with just a few changes, I can change my draw square into a draw circle. Do that 3 times with the same numbers. And, oops, I get an error. UL, sorry, don't go to UL, go to starting point now. I have a circular target logo, yay. Any questions about this function and this use of it? Does that make enough sense? Because I'd like to do something. Notice that these calls to draw a square look exactly the same as these calls to draw a circle. There is no real difference. So let's generalize our target drawing stuff. Let's do it like this. Let me show you where I'm going with this. Let's make a draw target logo function. Given a center and something else. And the idea is, instead of drawing a square or a circle, we'll draw whatever shape the user gives us, and we'll draw a target logo with that shape, passing along the right stuff, of course. So instead of draw a square or draw a circle, because it's the same every time, let's make it draw a shape and have the user tell us which shape they want us to use for the target logo. So that can be a parameter. Draw a shape. Please, user, pass along the function you would like me to use to draw the target logo with. And look at what you can do with this. This is a bit weird because you don't usually pass functions to functions in C++ if you've learned another language. If Python is your first language, this is exciting because this shouldn't be weird. Watch what you can do. Draw a target logo sitting at 0, 0, using draw square. Look at what this does. It draws the square target logo because it's going to pass along draw square as draw shape. That becomes a function that I can call in here. And I use that draw shape function 3 times with the center. Oh, sorry. I want to use the center that was given to me. Center, center, center. Red, white, and red. So I could just as easily now duplicate this and say draw target logo using draw circle. It'll jump here and call draw circle because that's what draw shape will be set to now. Draw circle 200, 125, 50. Just as easily. Ooh. Now I can draw both of them on the same screen. I can be like draw at 150, 150, the draw square target logo. Draw at negative 150, negative 150, the draw circle target logo. It all works out. You can pass functions to functions, and that generalizes our drawing of the target logo. Does that make sense? Are there any questions about that? That's a very powerful concept. Just for fun, let's make a triangular target logo now. We'll do it like this. Let's do draw target logo finally at 0, 0 again, using draw a triangle as the shape. If we want to use it like this, it needs to take those three things, the center, the width, and the color. I guess it's going to be a bit similar, more similar to draw a square than draw a circle. Let's make a draw a triangle function. We have the center x. We want to start our triangle at an easy way to draw the triangle, right? If it's an equilateral triangle, it's to draw it right here. So get to the bottom left. And given the center of our triangle, the way to get there is you go down by width over 2, and then, you go down by width over 3, and you go left by width over 2. It's a weird way to draw a triangle. That's how you, that's where the center is relative to the corner of a triangle. There's a 3 involved rather than a 2. It's interesting. So that's where the bottom left is. So instead of UL, it's called BL. That's center x minus width over 2 and center y minus width over 3. Oops. Go there, set heading 0. So if we're at the bottom, we want to go forward, turn left by 180 over, or 180 minus 60, and do that a bunch of times. And I believe that should draw us our equilateral triangle. So that should do it. With the color that we chose, of course. Begin, fill, and fill. Set the fill color to color. So that's how you can draw a triangle with a given center, from this center with this width, with this color. And yeah, that should do it. Now we can draw a target logo with draw a triangle. And now we have 3 target logos. We have generalized things. Oh, sorry, I used UL again. I called it BL. We want the bottom left. So go to BL. Oh no, looks like I drew it upside down. That's a cool little logo though. Let's fix that and then that'll be done. Let's see, what did I do wrong here? So I want to set heading 0. We do want to go east once we get to that spot. Go to bottom left, set heading 0. Center y minus width over 3. Forward width. Oh, that's why. It was supposed to be turn left. Because once you're here, you want to turn to the left, not to the right like we were doing with squares. Excuse me. So it's left by that. Left by that. And that should finally give us a triangular target logo, just in case we wanted one of those. But we generalize. So this draw target logo function takes a center and a draw shape function, and it will draw a target logo given the shape that we pass along and the center that we pass along. Any questions about that example? It's a fun one to study, I think. When in doubt, when you see a pattern like this, usually you can wrap it into a function. That's what we just did. We generalized. We made a function that took functions as parameters, which is really cool. All right. Those are the main examples that I wanted to show us today that had, I don't want to say value, but that had some sort of knowledge that I wanted to pass along to you. The final programs that I want to show you are just some cool things that I think you would enjoy to show you the power of what you can do with the Turtle library. And maybe this will help you on your programming journey to study this code. So let me do some stuff. Let me copy this in from last time. This would have been F22, I guess. I have 2 fun examples. I have this one and I have this one. Oop. So let me open both of them in theory. It will all work out. All right. So first silly example. Cool examples I may not have had time to get to in class, and I didn't. Just some more examples of like turtles and functions and things, just to show you the full power of all this. So have you seen this artist before? His name is Pete Mondrian, I think is how you pronounce it in English. Let's make this kind of artwork with Python, randomly. Let's randomly make something that looks like this. So it's a bunch of squares and rectangles and things with red, white, black, blue, and yellow, and a bunch of different lengths, okay? It's pretty complicated, but here's the algorithm that I came up with to draw this. So if you analyze this artwork, you can see that it's made up of a bunch of lines. A bunch of lines that are maybe combined, like it combined all these three lines together to build this inner square. But there's an underlying grid that it's working on, that this artist was using, I would say. And so if you just make a bunch of lines and connect some of them, you can, like, all right, I'll connect these three and these three, and then I'll draw a red square there. I'll connect these two with this two, and then I'll draw a yellow square there. That's the idea. I'll connect these four lines, I guess, with these three lines on the start, and I'll draw a blue square there. That's the algorithm. That's how you can draw this kind of artwork. So in essence, you need to pick these lines first. Let's pick those lines randomly. Pick a bunch of horizontal line locations and vertical line locations. Apparently, the canvas that this dude liked to use was 3x4, so we'll make a 3x4 canvas, maybe 300 by 400 or something. Let's draw 6 random vertical lines and 8 random horizontal lines, because there's more horizontal space. And then let's draw them all and eventually overwrite them with squares. So forever, pick 2 random horizontal lines, like, I don't know, this one, horizontal lines. No, these are, I don't know, let's call these horizontal lines for now. These two, and then pick 2 random vertical lines, this one, and then draw a square between those bounds with a random color. Like this one would have been randomly chosen to be red, for example. That's the bounds of a rectangle. And then you can like crop off the edges. It's really just a fancy use of the draw rectangle function that we've been using this whole time. So let me show you the code. It's pretty cool. Again, I would never dream of testing you on something like this. It's just a fun little example. But yeah, it's essentially draw rectangle with an upper left, a width, a height, and a color. Here's how you can draw a line from a start to an end location. Just go to, essentially. Pick a random color. Red, yellow, blue, black, and white. Trying to prioritize white because there's a lot of white in this artwork. More so. And here's our 3x4 drawing. Bounds. We'll make a bunch of we'll make 6 random vertical lines with random locations. Random horizontal lines between a range. And yeah, that's essentially it. Draw them. And then as long as the user wants us to, we'll pick a random like pair of horizontal lines, a random pair of vertical lines, and draw a random box there. And at the end, we'll just crop off our edges. But here's what it looks like. So it picked a bunch of random lines to draw. It won't let me resize this until I press enter. Gosh, that's going to be hard. So I press enter. Oh man. That's unfortunately a quirk of the way that it's programmed. It like stops the program and it won't let me control the window. Oh, there it goes. That still won't let me control it. It's a little too small for this screen, but that's okay. It picked a random box to draw, a random box to draw, random box to draw. And eventually it's overwriting them. And you can stop it whenever you want, and eventually it will be beautiful artwork that looks like that artist. So yeah, that's how you can do that. Oh, once it's done, I guess it will show me. It will allow me to resize it. But yeah, that's the idea. And it's different every time. It's random. But it's just a bunch of random horizontal lines, vertical lines, and you can control it. You can control it. You can let it do a bunch of stuff. There it goes. And stop it whenever you want. Press Q when you're done with it, when you're tired of it. And then that is your artwork. Beautiful. Yeah, so study this code if you'd like. It's a fun little example of like a slightly complicated algorithm, I would say. And for my last example, just for fun, you know how people like to wear the shirt with this Joy Division album cover art on it? This artwork is actually just data. This is data taken from, I have this program here, it's taken from a celestial body, from an oscillation signal coming from something called a pulsar. I don't have enough physics background to know exactly what that is, but it's some sort of thing in the cosmos that like emits some sort of electrical signal, I guess. And we can read that here on Earth, but back in the 60s, they took a few readings of this pulsar, every pulse of it, and if you plot that in a cool looking way, you end up with this graph. And we can draw that graph from the actual data. And so here is the data. It's just a list of lists, one for every pulse. So it's a list of a bunch of lists of little numbers. Like, all right, here is the strength of the signal. Negative this, negative that, negative that, negative that. Then it gets a little bigger, little less, little bigger, little less. And that will draw like the peaks and the valleys. And if you hook into this, you can draw that album artwork that all the cool kids like to wear. You just use these as your offsets and start drawing a bunch of, just tell the turtle, go up, go down, go up, go down. It really is a little bit more complicated than that because you want to like overwrite the previous lines. If like when you're down here, you want to, maybe you had some stuff down here, you want to fill in from top to bottom so that all this stuff, I don't know if you can see that very well, but like you need to fill it in there to overwrite what used to be there. But again, it's draw rectangle strikes again almost. I'll draw a black rectangle, and then instead of drawing like lines or things, I'll make a draw polygon function to use all those points that I was using. That's made up of calling draw line a bunch of times, I would guess. And then draw fuzzy line goes from some starting point to some ending point with the signal that we're given. So if you study this, I gave enough comments to hopefully let you understand it. I could not begin to explain it very well, but go through the signal and like draw a fuzzy line made up of that signal and use the turtle to do it. When you do it, here's what happens. There he goes. You can take that data and have the turtle plot all the points, drawing lines, drawing filled in polygons essentially each time, overwriting what used to be there. I turned the turtle, his speed on super fast, so he kind of skips over some stuff, because that would have made it even slower. It's not the most efficient thing, but at the end of this, we will have that exact album cover. It will look exactly like that, I promise, and it'll just be glorious. It's getting there. But yeah, this was not just something that was made up. It was actual data, and we can plot that data. We're just making a fancy graph using the turtle library. That's all. There he goes. Slowly but surely, he's getting to the bottom. But yeah, I use those offsets to draw a bunch of polygons. So like draw a line from here to here, essentially. From here to here, from here to here, and fill it in. Fill it in so that we're overwriting what used to be before us. Almost there. Just a few lines left, it looks like. And it really is exactly the same. I think your computers could have done this a lot faster than mine. But at the very end, you get... Come on, little turtle, you can do it. So close. At the very end, you get the exact drawing, plus a little extra turtle in the bottom right. My computer is too unhappy to show it to you, though, I think. Oh, he's not done yet, that's why. Are you happy now, turtle? Yeah, I think that was it. So, yeah. Just shows you that you can make some fancy stuff with Python and a little bit of thought. And you get a cool picture with the turtle in the bottom right. Any questions about that? Probably I would direct you to the code. I'll give you all this code. I would not dream of testing you on it, but it's cool. Yeah, that was my last silly example, I think. Any questions about anything we did today? Obviously, I would not dream of testing you on these examples, but I just wanted to show you how far you could go if you wanted to. All right. So yeah, that brings us to the end of class. That's the end of the last lecture. How exciting. We made it to the very end. Remember when the final is? We'll go check that right now. So we are going to be in this room when? It's either Monday or Wednesday. I've already forgotten. It's Wednesday. So we'll be here on Wednesday of finals week, Wednesday next week at the same starting time as class. It'll just be an hour and 50-minute final because that's how long finals get to be, apparently. All right, so that's when that'll be. So I'll see you then. And yeah, thanks for putting up with me throughout this class. Thanks for a good semester. And I think what I'd like to do, because the point of this class, because it's a GE class, you're not required to be a CSCI major to take it. If you liked what you saw, please consider becoming a CSCI major. I'm supposed to poison your mind a little bit and try to get more people into the program through this class. So if you're not already a CSCI major, but you liked what you saw in this class, consider taking CSCI 40. So yeah, that's all that I got for us. The rest of the time is yours to work on whatever final things need to be worked on.